Hi guys and welcome back. I know this is going to be an amazing grade 12 show. We've got Shanae with us and don't forget that we will be answering your questions on the Facebook page and on Twitter. She'll be here and we'll be typing ever so quietly. And that's on facebook.com/learnextra. Also chat to us on Twitter @learnextra. And now for that favorite part of your day, Tracy, take it away.
Oh, Indy, I knew there was a reason why I liked working with
obviously.
you. She's so sweet. So nice having
Teacher's pet.
Shanae here.
Oh, thank you.
Great.
Hey.
Just so you know, Shanae, I saw her, I actually met her at Expo last year, so she's a good girl. We like that one. Okay. Anyway, we need to get back to the science. So grade 12, what we're going to look at is, last week we looked at the chloralkali industry, now we're going to look at the fertilizer industry. These are one of your guaranteed questions, okay? There's 3 important processes we're going to look in today's show. We're going to look at contact process, the Haber process, and the Ostwald process. And if you don't know the Haber process by now, you've been sleeping through science for the last 2 years. But why is the fertilizer industry important? Well, first of all, we all realize we have an increasing human population, which means we then have an increasing need for food. So we need to be able to make more food with less land. So we've got to make it more efficient in what we're doing. So this becomes a real problem for us. That's where fertilizers come in. Now, when it comes to our plants have 16 basic nutrients. Now, I know this is quite a big, and it's quite small. I'm sorry, grade 12s, but I just wanted you to get an idea. And we're not going to spend too much time on what all the different nutrients and stuff do. But basically what it comes down to is we have mineral nutrients, and your mineral nutrients are nitrogen, phosphorus, potassium, calcium, magnesium, sulfur, all of those sort of things. And you have your non-mineral nutrients. Now, non-mineral nutrients are hydrogen, carbon, and oxygen. Now, hydrogen, carbon, and oxygen come from the air. They produce it during photosynthesis, so we're not too worried about those. We then come to our mineral nutrients, and we get what we call macronutrients and micronutrients. Now, our micronutrients are the ones we only need in very small trace amounts. It's not like we need hundreds and hundreds and hundreds of kilograms of it. Our macronutrients are nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. Those are the 6 important ones. But even our macronutrients are then divided into 2, into primary nutrients and secondary nutrients. Now, secondary nutrients are calcium, magnesium, and sulfur, and generally our soil has enough of that. The issue is our sodium, potassium, and phosphorus. Those are the primary nutrients. And when we look at fertilizers, we have to look at how we get those three fertilizers, okay? How do we get the nitrogen, the phosphorus, and the potassium? Because we can't just go and take phosphorus as an element and dump it in the ground and hope for the best, because that's not going to help us. Same with potassium. Hopefully you remember from grade 10, if you put potassium in water, potassium explodes. So putting potassium in soil and wetting it, bad idea, I think, generally.
Does it make an explosion?
Have you never seen potassium in water?
No.
We're going to have to...
You see Shanae goes, oh, I knew that, obviously.
No.
Didn't you?
No, I'm not a genius.
This is good to know.
You know, it's probably she's got a teacher that's like me, and we don't do such things because we tend to blow things up. So we just don't like getting hurt.
Tell us more, Tracy.
Actually, if you didn't know, potassium's what they use for underwater flares. That's the element they use in underwater flares. It burns in water. Yeah, it's very cool. It's that nice purple. It's got that beautiful. It's almost like the same color as the set behind us at the bottom there. It's got a beautiful violet,
back there.
purple. Anyway, moving on. The point is, we can't just put it in the soil. Okay, so we're going to spend a lot of time today looking at where we get our nitrogen-based fertilizers. Phosphorus and potassium are a little harder to get. We need to use our superphosphates. Potassium and that sort of thing comes from bone meal. There's lots of ways we used to get natural fertilizers, but obviously these don't really work for us. Potassium and phosphorus used to come from what was known as guana, which is basically bird poo, okay, bird excrement. And before World War II, that was generally enough. But as the world's population has exploded, that's not. And also, before World War II, we used to get a lot of our fertilizers, our phosphorus and potassium fertilizers from bone meal, which is exactly what it says it is. It's ground up animal bones. But our population is growing too quickly, so that doesn't help us. We've got to look at artificial ways of getting fertilizers. First thing we're going to look at is we're going to look at the preparation of ammonia. Now, grade 12s, I really hope that when we look at ammonia, none of you are going to be going, I've never seen that before, because you should have done the Haber process in grade 10, and you most definitely should have done it in grade 11. So we're now going to look at it in a little more detail, because we know that we start with nitrogen, hydrogen. Okay, I'm sorry, my picture's a little strange. It's always hard to put these pictures in for me. Now, what do we need to remember when it comes to the preparation of ammonia? First of all, where does the nitrogen come from? Well, the nitrogen that we put into the system comes from the liquid distillation, the fractional distillation. There we go. Let's write this so that you can read it. Oh, really? Really? There we go. Man. See, I told you the board doesn't like me.
The board loves you.
No, it doesn't. Okay. The nitrogen comes from the fractional distillation of liquid air. Okay? So we get nitrogen from the air. Remember, the atmosphere around us is 78% nitrogen. So what we do is we take air from the atmosphere, put it under extreme pressure, very, very low temperatures at like minus 200 degrees, and it slowly heats it up. The pressure makes it a liquid. It's heated up to from about minus 196. The nitrogen comes off, so then we can take the nitrogen gas off and leaves all the other gases behind. So, I mean, it's minus 196. It's a little cold. Anyway, hydrogen comes from the air as well. Okay? So, fairly easy, nothing difficult. We also get hydrogen from when we crack methane, natural gas. Okay? So, we can take methane, it gets cracked, we add it to water, which is what we do with it. And this is just another process for it. And we end up with carbon monoxide. Not a good idea, but it's okay. We'll live with it. And hydrogen. Okay? But we'd prefer to get it out the air. Nitrogen and hydrogen come together. They get mixed. They then get compressed. This is where you've got to remember certain information like. Okay. We have this at high pressure. All right, so this is what the compressor is for, and high temperature. Okay? We've got to look back, well, relatively high temperature. We've got to look back at our equilibrium reaction, because the reaction for ammonia, when we have hydrogen plus nitrogen, then gives us ammonia, it's a reversible process. It can get to equilibrium. So in terms of our economics, we've now got to make sure that we can get a fast enough yield, okay, within the right context. So we look at this and we go, well, if I increase the pressure, and I didn't write this as a balanced equation, so that's always a good idea. We want to do it at a fairly high pressure, because at a high pressure, we're going to favor making the NH3, but high pressures can be very, very expensive and very, very dangerous. So it's done at about 200 atmospheres, which isn't actually that bad. And we would also want to do it. This is a very exothermic reaction. So I'm just writing over the grade 12. It's minus 92 kilojoules per mole, which is your delta H. So we want to do it at a low temperature, because a low temperature favors the exothermic reaction. But if we take the temperature too low, then it goes too slow. And we all know the saying that time is money, and it's the same in industry. If it takes too long to get the ammonia, then that defeats the object, because it's going to cost us too much money. Okay, so we mix the nitrogen and hydrogen, goes through a compressor, helps us increase the temperature. We then, increases the yield. We send it through to a converter with a catalyst. Remember, this does have a catalyst in it. We would use nickel, probably. Okay, goes through the converter where it's cooled down again. By cooling it down, we get it to a liquid state. At that liquid state, we can then actually remove the NH3, because the NH3 will come off first, which is what we want. We want the NH3. That's the whole purpose of this. Whatever nitrogen and hydrogen's not used gets put back into the system, and we start again by putting nitrogen and hydrogen in, goes through the system, and this is nice because it's more of a cycle, so it makes it easier and we can reuse the hydrogen and nitrogen. From here, this process of making the ammonia is the first step in a chain of ways of making our nitrous-based fertilizers. Nitrogen in our fertilizer is very, 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 very important, okay? Now, in terms of our conditions, this is temperatures around 400 degrees. Pressure, I said, was 200 atmospheres. And the catalyst that we use over here is iron, or iron 3 oxide. Okay, any one of those, in general, it's a mixture of the both. Grade 12s, you must know the conditions. It's not just enough to know this reaction. Now, this has the title, let's write it somewhere where it's not going to look like chicken scrawl, of being the Haber process, which I know I say incorrectly because it's actually German. What's really exciting about this grade 12s is we're one of the few countries in the world that's allowed to use this process. It's actually known as the Haber-Bosch process. It was developed by some Germans, okay? Haber is the one who got the chemistry right, and Bosch is the one who got the setting up the whole factory and stuff and all of those sort of processes and actually got that correct. And between the two of them, we call it the Haber-Bosch process. We're one of the few countries in the world that's licensed to use it, which is actually a good thing for us, despite everything else, and we've been allowed to use it for years and years and years and years and years, which is actually amazing, because we've done the same with other processes. Sasol, we all know Sasol produces a lot of our petrol. Sasol has a process called the Sasol process. Look at that. Very inventive with that name, which is a way of producing petrol from coal. Now, we had to learn to do that because during the 70s and 80s, with all the embargoes and everything else, as protest against what was happening in our country, we had to find a way to get petrol because we couldn't get enough oil. That's when the process got developed, where we could take our coal reserves and turn it into petrol, which actually, despite all the complaining, and I know I'm one of them, we still have some of the cheapest petrol in the world per litre if you compare to other people. And I have family who live in the UK, and I mean, they're paying, last time they looked, they're paying like 14, 15 rand a litre, so I'm not going to complain ever again. But Sasol has recently licensed the Sasol process to China. So that means our engineers go over, China pays a licensing fee, brings in foreign exchange. We do the same with the Haber process. So it's all well and good. We like
It's
Sasol.
interesting.
Yeah, all these things that you didn't
Not
know.
the Indiana process. Probably the Chenet process.
That's
at
what I think
some
the
point.
toothbrush thing's going to be. I might never touch a toothbrush again unless it comes out the packet after what she just said. You know, new toothbrush every day could get a little expensive.
Exactly.
Yeah, let's not go there, hey? All right. After the Haber process, another good fertilizer, which we're not going to spend time on, is urea, which is exactly what it sounds like, okay? In fact, I'm hoping you know this story. Urea is quite interesting because before the discovery of how to produce urea, organic chemistry was defined as being the study of living organisms, and the compounds in organic chemistry had to come from a living or a previously living organism. So it had to come from a human or an animal or a plant. But then, about 100 years ago, and I can't remember his name right now, but someone went and produced the urea molecule from two inorganic compounds. And now the scientific community went, okay, we have a problem because we know what urea is, but it didn't come from an organic compound, from an organic living thing. So they changed the definition of organic chemistry to be the study of carbon compounds. All these things. A little bit of useless information for today. It's always important to have those. So we get on to how we make ammonium nitrate. Really, really important one for us. We've discussed the Haber process, so now we need to discuss the Ostwald process. And the Ostwald process is how we make nitric acid. Okay, and I don't think I'm going to get through all of it before we take a break, but we'll go through as much as we can. Now, the Ostwald process happens in 3 steps. You must know these steps, and you must know the equations that go with it, grade 12s, that's very, very important, because often what happens is these will be given to you in a flow diagram type situation where they miss out some of the reactants, or they miss out the product or whatever, and then they're going to ask you about it, so make sure you know it. Now, the first step is to take the ammonia, and we react it with oxygen. Okay, step 1. It's very, very exothermic, minus 950 kilojoules per mole. That gives us nitrogen monoxide. This is also done in the presence of a catalyst, which is platinum. I want you to note something here, grade 12s. These are not reversible reactions, okay? So we're not considering equilibrium conditions. We add in the catalyst because we want to increase the rate. Then, second one, step 2 is we now react our nitrogen monoxide with oxygen, and we get nitrogen dioxide. Step 3, we take the nitrogen dioxide, we dissolve it in water, essentially. There's a couple of equations associated with this. This is the most important one. We get nitric acid as an aqueous solution, and we get nitrogen monoxide gas. Obviously, the fact that we get nitrogen monoxide gas at the end is actually a problem for us, but this nitrogen monoxide gas can be recycled into step 2. So when we look at the process, and I have a schematic diagram for it, there we go, we can actually take the NO out, the NO2 out. So we have air and NH3. The air gives us the oxygen. Okay, so the reason why we want that is we want oxygen. We go through a purification process. That means we get rid of all the extra little things that we don't actually want. This is where step 1 takes place. Okay? Step 1 is also known as the catalytic, lots of words for you, oxidation of ammonia. Okay? And now you all go, no, we know why it's called catalytic oxidation, because we use a catalyst. Okay, that catalyst is platinum. And the catalyst would be like those little lines over here. That's my catalyst over there. Then, once we've got the oxidation, the NO comes through. Over here, we're going to add in some more oxygen. We take it through some cooling places. We then put it through water. These are glass beads. And basically what their function is to mix the NO2 gas and the water together to give us the HNO3. The schematic could include a place where we take out the NO gas that's been left and we recycle it into the middle of the process. It all depends on how the factory is set up as to where we're going to do that and why we're going to do it. Also, we can prevent getting NO, because if instead of just having water at that bottom one, we can, if we add the NO to oxygen as well as the water, what happens is we actually just get nitric acid. So it all depends. If we don't have the oxygen, we end up with nitrogen monoxide at the end, and that needs to then go back into the process. But if we add that oxygen, we can get to nitric acid straight away. Now, we need the nitric acid because if I take the ammonia, is what we said earlier on, we take ammonia, NH3, add it to nitric acid, I get ammonium nitrate. So the ammonia right at the beginning is really, really important. Okay, but I've got to use the ammonia to make the nitric acid to then react it with the ammonia again. So a lot of companies will actually do the entire process. They will start with the ammonia because all our fertilizers start from there. So they'll do the Haber process, and then they'll use the ammonia they make to make, in this case, ammonium nitrate. We can look at ammonium sulfate, we look at ammonium phosphate, a whole bunch of things, but we'll add it to the nitric acid once we've got that done. And I think, grade 12s, we can take a break there, Indy, because I've got another process to do. So.
Okay, let's do that. Okay, as you can see, the computer is facing Shanae, and she is asking all of your questions. So please keep them coming, guys. Let me know and let her know if there's anything that you are wondering about. And let's not forget about Tracy, because we don't want her to get upset. If there is anything that you aren't understanding that Tracy is going over, please make sure that you do post it on our page too. Who knows, maybe even Shanae can give them a bash for us. So what we'll do is we'll see you now after the break.